Now, it was very helpful that I had this picture ready to go when I was given this problem. It tells me right away that the function y equals e of x is the upper boundary of my region, and the function y equals x is the lower boundary of my region. When we are given these problems from scratch, we might not always be given a picture. This is a very important tool, though. So if we're given a problem, I would say the very first thing to do is to make a rough sketch of what we've been given. So here is another picture. And this time, I don't even know formulas for the two different functions. The slide is calling these yt for top and yt for bottom. And it's very important to know who's on top and who's on bottom. If you get it wrong, then there will be an extra minus sign in the integral. We always expect these calculations to be positive. Now, notice that there's a very natural place where my pink curve yt meets the blue curve yb. And this is at x coordinate a. On the other side here, we're just stopping the integration at some arbitrary coordinate x equals b. So when we work on these area problems, we might actually need to figure out those crossing points. Here's some more information about Riemann sums, but I feel that I got that pretty well in my previous video. You can pause here if you like. I want to move on to a question where we need to actually calculate these intersection points. Yes. In this example, both the side boundaries are a single point. Rather, I should say, each of them is one point. The first step for finding this integral is to calculate a and b. So here is an example of one of these problems. Find the area of the region enclosed by parabolas y equals x squared and y equals 2x minus x squared. Now, before I even move to the next slide, I want you to imagine what these parabolas look like. The one of them, y equals x squared, is an upwards facing parabola, which I know because the lead term has a positive coefficient. The other of them I know is a downwards facing parabola, and I know that because the x squared has a negative coefficient. So I've got my happy smiling parabola, I've got my sad frowning parabola, and I'm expecting to find something like a football shape in between the two of them. So when I'm asking for the area of the region between these two parabolas, it's that area that's stuck in between is what I'm asking for. So, there's still no picture on this slide, but I can calculate those points of intersection straight from algebra. So points of intersection will mean that I have the very same y coordinate for the very same x coordinate. So I'm going to set those functions equal to one another and solve. So now, putting them together, I've got 2x squared minus 2x equals 0. And I can factor out an x. This equation reduces to 2 times x times quantity x minus 1, all equals 0, which makes it pretty clear, at least to me, my solutions are x equals 0, x equals 1. Those are going to be my two boundaries for the integral. And if the functions are overlapping at x coordinate 0 and at x coordinate 1, why then they must be sharing y coordinate 0 and y coordinate 1. How did I get those y coordinates? I just put my x coordinates back into the function. So here is that picture I was promising. The blue parabola is my upwards facing parabola. That's y equals x squared. The pink parabola is the downwards facing parabola. That's 2x minus x squared. And as promised, I've got sort of a football shape between them. And we are going to integrate to calculate how much area is in there. Bear in mind that I still need to know which of the functions is on top. So from this picture, I can see that the downwards facing parabola is the top function. And that should make a little bit of sense thinking about the ways that these functions can overlap with one another. I could have also determined that algebraically. How do I determine that algebraically? Well, I just pick some coordinate x, let's say a half. The one parabola tells me that y equals x squared, so my y would be a positive 1/4. The other graph tells me y is equal to twice x minus x squared, so there I would get y equals 3/4. And I know that 3/4 is greater than 1/4. Okay, so that's the reason why 2x minus x squared is the top function and x squared is the bottom function. From this point, all I've got to do is set up my integral. Again, it's just the difference, top function minus the bottom function. So here it is, my area is equal to the integral from 0 to 1 of the function 2 times x minus 2x squared, all dx. And again, at this point, it's just integrating a polynomial. I find that the answer to this problem is that there is 1/3 of a unit of area sandwiched between the two different curves.